Welcome you all to the lecture series of Digital Electronics QE 039/049. Myself Dr. Kishanu Kundu, Assistant Professor, Department of Electronics and Communication Engineering, GL Bajaj Institute of Technology and Management. So, we are discussing about digital logic families, and this is the part 3 lecture of the same topic, digital logic family. In the previous parts, in part 1 we have discussed about digital logic family and characteristics of digital logic families. Okay. In part 2 we have discussed some examples of digital logic family like RTL, DTL and DCTL. So, in part 3 we are going to discuss two more examples of digital logic family, that are TTL and ECL. So, let us proceed. So, first of all we will discuss about TTL, transistor logic. Already in the previous lectures we have discussed about RTL, that is register transistor logic, DTL, diode transistor logic and DCTL, diode coupled transistor logic. So, now the turn is for transistor logic, that is TTL. So, transistor logic belongs to the digital logic family. It consists of transistors at both input and output sides, diodes and few resistors. Okay. Unlike resistor transistor logic and diode transistor logic, both the logic function and amplifying function are performed by the transistors. Okay. The TTL integrated circuits are very popular in different applications, including computer controls, consumer electronics, industrial control systems and etc. So, TTL are having application in these areas like computer control, consumer electronics and industrial control systems. Most TTL circuit have some type of totem pole output configuration. So, what is totem pole output configuration? We are going to discuss in the next slide. Here we will be having the three configuration: totem pole output, open collector output, tri-state output. Before that we will discuss a normal TTL logic and then we will come to this lecture. So, let us start discussing about a TTL logic, and this time we are going to implement NAND gate. Okay. So, you know what is the output of NAND gate? When both the inputs are low, the output will be high. If any one of the input is high, output will be low. This is the logic of NAND gate, and now we are going to implement this same NAND gate logic using transistor logic. Okay. So, you can see from the diagram itself, it is a diagram of 2 input TTL NAND gate. It has 4 transistors Q1, Q2, Q3 and Q4, total 4 transistors Q1, Q2, Q3 and Q4. Transistor Q1 has 2 inputs. Here you can see a 2 input transistor. Till now these are all are 1 input transistor, but here you can see 2 emitter side is there, right. This is called 2 input on the emitter side Q1. Okay. Transistor Q3 and Q4 from the output side. So, Q1, Q3 and Q4 we have taken output between the Q3 and Q4, and this is called the totem pole output. This is called the totem pole output. Okay. Now, the circuit of 2 input NAND gate may look complex, you can see, but we can simplify its operation by considering the diode equivalent of the 2 input NPN transistor. Okay. Here you can see this part we are going to simplify, Okay. So, let us check how we have simplified that. We have taken diodes. Here this dA and dB represent the 2 input emitter junction of transistor Q1. Okay. So, Q1 can be replaced as 2 diodes. Again for Q2 we have taken another diode. Okay. So, you can see dA and dB represent the 2 input emitter junction of transistor Q1, diode DC represent the collector base junction of the transistor Q2. This is DC, this is D suffix C, and this is for Q2, and these two are for Q1, these are for Q1. Okay. This is the simplification we have done from the previous circuit. Okay. Why we have taken this consideration? Let us check. So, when both the inputs A and B are low, we know that this is plus, this is minus of diode, right. So, see, if we are giving 0 0 means this is forward biased, okay. Both the diodes are forward biased. So, both the diodes are forward biased. So, the current due to supply voltage VCC will go to the ground through R1 and two diodes DA and DB, right. The current will be going like this, forward biased, okay. These two diodes are in working mode, open close switch, on, you can say forward bias, on switch, close switch, anything you can say, right. The supply voltage gets dropped in the resistor R1 and it will not be sufficient to turn on the transistor Q2, means here you can see that this is the supply voltage is coming here, like. So, we have taken up to this part only. So, this is the supply is coming. So, this current will be going like this, no current will be in this part, no current, this current will be in this part. So, this what will happen? So, no transistor current will be going to the Q2 and Q2 will be open. So, if Q2 is open, the Q4 will also cut off, means you can see from the diagram when Q2 is open. So, it is cut. So, this like this it is also cut, right, because this current is going to the base of Q4, right. So, as Q2 is cut, so Q4 is also cut. So, what will happen? Since Q2 cut, but the transistor Q2 is pulled high, Q3 is pulled high. Here you can see that Q3 is pulled high, because this current is also going to this, as this current is going to this side, I can change the color, you can easily understand. This current is going to this side. So, this current is also going to the base of the Q3, but there here no current, but current is going to this side. So, it will make Q3 as high, it will turn on Q3. Since Q3 is a emitter follower, the output at the terminal also will be high, which is our logic 1. So, if Q3 is high, then logic 1 will go to this current. Now, this is forward biased. So, current will go, this will on. So, this will go to Y. So, Y will be 1. Got it? When both are 0, then what will happen? This current will be go to that side, but current will not, current will come to Q3, Q2, Q4 off, but Q3 will be on and Q3 will be on. So, its current will make this diode as already is forward bias condition. So, diode will be in on and it will be acting as a closed switch, as a result Y will be 1. Okay. When any of the input either A or B is low. So, if any of the input is low, then that diode will be low, input will be forward biased and the same operation take place as explained there. In this case, the output will be high. So, in all three cases we know that NAND gate, if all the three any of the input is low, then output will be high. Okay. So, but the condition when both are 1, when both are 1, here if both are 1, we are giving high voltage, here we are giving now high voltage. So, what will happen? If both are 1, so both are 1 means this diode will be not conducting, reverse biased, right. The diode will be reverse biased, the diode DC of the cutter bus junction is forward bias. But here you can see if these are not working, but the current will come to this side. So, now what will happen? DC will be working, now DC will be working. So, current and it is getting the base will be getting the current. So, Q2 will be on, as Q2 will be on, as Q2 will be on, as Q2 will be on, then what will happen? Q2 will be on, so Q4 will be on and output is connected to the ground. Okay. So, output is connected to the ground, Y will be 0, clear. So, we can see that when both the inputs are high, Q2 will be turned on and transistor Q4 will be turned on. So, both the transistor, the output side will be conducted. So, the output terminal will be at low volt, which is considered logic 0. Okay. Already I have taken that if Q2 is on, so Q4 will be also on, and Q4 is on means it will be a closed switch. So, output will be connected to the ground. So, output will be 0. So, it is perfectly giving the truth table of NAND gate. Okay. So, now we are going to discuss the output configuration of TTL logic. There are 3 different output configuration. First one is totem pole output, then open collector output and tri-state gate output. So, let us discuss. This is the totem pole output. So, in totem pole, what will they, just whatever we have discussed so far, that only we are going to discuss here. Okay. So, in the circuit shown, the shaded portion shows the totem pole output. This is the totem pole output. This shaded portion is nothing but the totem pole output. Okay. Here we are having 4 transistor Q1, Q2, Q3 and Q4, one diode D. So, as we have discussed in the previous slide, that to make it a simple one, what we do, we represent this transistor with 2 diodes D and DB. Okay, and here for Q2 we are having one diode that is called DC, right. So, the transistor here what will happen, transistor Q3, Q diode and Q4 and the current limiting resistor R3 from the totem pole output configuration of the TTL. See, this is R3, this is Q3, this is D and Q4. Okay. So, these are the 4 components of totem pole output circuit. There are few advantages of using this configuration. So, let us see what are the advantages. So, first of all, when the output switches from low to high state, the output transistor Q4 goes from saturation to cutoff. Means when the output is moving from low to high, then what happen? Q4 goes from saturation to cutoff. During this transition, the load capacitance across Q3 charges exponentially from low to higher voltage. Okay. As a result of this, the load capacitance across Q3, charges exponentially from low to high voltage. Due to the low output impedance of both transistor Q3 and Q4, the output voltage can change quickly from low to high value as the capacitance change and discharge quickly. So, these are the advantages of totem pole output configuration, you can see from the diagram itself. Okay. Next, then open collector output. What is open collector output? You can see that we have taken again for 3 transistors Q1, Q2, Q4, Q3 is missing here. Okay. And VCC is connected to directly R1 and R2, and here we are having one R4 resistor and this is the RL, external pull up resistor, but here we have removed the R3. Okay. That is why it is called the open collector output. What is happening here? The open collector output configuration of transistors and logic is shown in the figure. In this configuration, the transistor Q3 and pull up resistor is eliminated, right. We have already discussed. See, here we are having R3 and this pull up resistor, R3 Q3 and R3 as the pull up resistor. So, that 2 has been removed in this circuit, and here instead of external pull up resistor for proper operation as shown in the figure, here we are having a RL. Okay. The output is taken from the open collector terminal of Q4. So, we are getting output from this open collector input output Y, okay, open collector terminal. When transistor Q4 is off, when this is off, the output Y will be high, because if it is cut, then Y will be connected directly to this VCC. So, in this case Y will be high, and when Q4 is on, when Q4 is on, this is on, then this will be acting as a closed switch. So, Y will be connected directly to the ground, means Y will be 0. Okay. So, this is nothing but the open collector output. Next, tri-state gate output. While operating the transistor in this output configuration, it is possible to attain higher speed. This is the advantage of tri-state gate output. We are getting higher speed. 3 output state is possible: high, low and high impedance. When transistor Q3 is on, the output at terminal Y is high. The output is low when the transistor Q4 is turned on. The first and second states are the normal operation of TTL. Obviously, these are we have seen that when Q3 is on, Y is 1, when Q3 is on, Y is 1, when Q4 is on, Y is 0. So, this is the normal TTL logic. Also here also we have seen the same thing, when Q3 is on, Y is 1, when Q4 is on, Y is 0. Okay. So, this is the normal output of TTL circuit. In the third state, both the transistor Q3 and Q4 are turned off, which results in neither low or nor high output. This is the third state, when both the transistor Q3 and Q4 both are off. So, what the result? The result is neither low or nor high output. Got it? Very good. These are the advantages. This is the high speed operation. The propagation delay is around 10 millisecond, which is fast compared to DTL and RTL logic devices. When we discuss about RTL and DTL, we told that DTL is faster than RTL and DTL. So, how it is faster? As the propagation is around 10 nanomillisecond. Less power dissipation compared to DTL and RTL, low cost, better fan out and reliable operation for noise. So, these are the advantages of TTL logic in comparison to DTL and RTL logic. Next example of retail logic family is ECL, emitter coupled logic. Emitter coupled logic. So, emitter coupled logic, abbreviated as ECL, is the fastest of all logic families. Is the fastest of all logic families. It was invented by Hanon S. Yorke in the year of 1956 at IBM. It is also called as current mode logic. Another name of ECL is current mode logic. The design of ECL circuit consists of transistors and resistors. By preventing the transistor from entering into saturation, the high speed operation is achieved in ECL logic family. So, how we are getting better speed in ECL? The answer is by preventing the transistor from entering into saturation. It does not allow the transistor to get into the saturation mode, and that is the reason that ECL performs with a very higher speed. Very small voltage swing is necessary to switch between the two different voltage levels. This cannot be achieved in transistor logic, as the transistors are into saturation mode while in operation. So, the thing is that the voltage swing for switching between two voltage levels should be very small, but in TTL logic it is not achievable, right. it is achievable only in ECL, and that is why ECL is the fastest one. Okay. Emitter coupled logic family offers an incredible propagation delay of 1 nanosecond. Previously it was 10 nanosecond, 10 millisecond, sorry, 10 millisecond, but ECL is performing with 1 nanosecond. This is faster, right. The delay is more reduced in the latest ECL families. Once it is coming with new versions of ECLs, delay is more reduced. Okay. Good. So, now we are going to explain the inverter circuit of emitter coupled logic. Okay. So, here we are having supply resistor R1, R2, okay, and here we have taken one transistor Q1 and Q2, and this is the emitter resistance. Okay. So, let us check. It has 2 NPN transistors connected in differential single ended input mode. Both the emitters are connected together with common resistors Re. Here you can see that the emitter of Q1 and emitter of Q2 are connected with Re. Okay. It is the current limit resistance used to prevent the transistor from entering into saturation. Already we have told that as it does not allow to transistor to enter in saturation, but how it is not allowing to enter the transistor into saturation mode. So, this is the reason this Re is mainly responsible, because we have connected both the emitter of the transistors Re with the Re, and it is going to the BEE. Okay. It has 2 outputs, inverting output V out 1, inverting output V out 1, and V in is the and non inverting output V out 1 2. So, this is inverting output, and this is non inverting. This is non inverting. VIN is the input terminal, VIN is the input terminal where low or high input is given. You can see we have given either low input or high input. Okay. So, when the input is high, let us discuss when input is high. So, input is high means Q1 will be 1 on, when it is high Q1 will be on, right, but not saturated to and the transistor Q2 is turned off. If Q1 on, Q2 will be off, okay, and what will happen? This will pull the output V out to high due to the drop in resistance R1. The output of terminal V out will be at the low value. Okay. So, that is why it is called inverting, means here we have given 1, but output we are getting 0. So, inverted output, right. That is why it is called inverting output. On the other side, when input VIN is giving low, when VIN low, this is low. So, Q1 will be off, but Q2 will be on. Okay. V is low, turn off Q1 and transistor is turned on, the transistor Q2 will not enter into the this is Q2, transistor is turned on. Okay. But it is not, it will not allow it to enter into saturation, right. It will make the output of terminal V out to be pulled high, means here we are giving 0 and it is getting 1. So, again inverted output we are getting, right. Due to the drop of resistance R2, the output of terminal V out will have a low value. Okay. Got it. Now, next this is the example of 2 input ECL OR oblique NOR gate. Okay. So, you can check it out here, transistor Q1, Q2, Q3, R1, R2 resistance, Vn is given to the base of Q2, okay, and V1 we are getting two output. So, V out 1 will be giving the output of NOR gate, and V out 2 will be giving the output of OR gate. Okay. So, here additional transistor is used at the input side. Again another additional transistor we are using, previously only 2 transistor was there, here we are getting another additional transistor. Okay. So, you can check it here. The operation simple as explained above. If the input at both the transistor Q1 and Q2 are low, it will make the V out 1 will be high value. It corresponds to NOR gate output. At the same time, transistor Q3 is turned on, which will make the V out to be the low. It is corresponding to the OR gate output. I know that OR and NOR are complemented version, right. So, here we are getting the output for NOR gate, and V out 2 will be getting the output for OR gate. Similarly, if both the input of transistor Q1 and Q2 are high, it will turn on both the transistors. It will drive the output at terminal V out 1 to be low. The transistor Q3 will be turned off during this operation. It will be driving the output at terminal V out to be high. Okay. So, when both the input of transistor are high, that time V out will be 0. This V out 1 will be 0, but V out 2 will be 1. Okay. So, this is the NOR gate and OR gate output we are getting from the circuit. What are the pros and cons or advantage and disadvantage? High speed operation is possible, already you have seen. In the fast stage logic family, since transistors are not allowed to enter into saturation, which reduces the storage delay, and fan out capability is very high for ECL. Now, what are the disadvantages? For the fast switching of transistors, the low and high logic levels are kept close. It reduces the noise margin. Since transistors are not allowed to enter into the saturation, the power consumption is more. This is the again one big factor is coming, as the transistors are not allowed into the saturation mode, it causes more power consumption, though the speed is high, but power consumption is more. So, like that it is having the advantage of high speed, but disadvantage of having more power consumption. Okay. So, these are the references, and thank you.